This was the beginning of database management systems, programs that run on a database server and accept and process high-level commands that instruct the computer which data to return. These systems take care of file management. At the same time, and most importantly, they ensure the consistency of logical units of work composed of multiple changes, as well as the overall consistency when several users are concurrently accessing and modifying the same data. The first database systems required painful crafting, and even minor changes to the structure of the database were nightmarish. Around 1970, an IBM researcher, Edgar Codd, had the insight that database systems could rely on mathematical foundations that would transform the craft into a science. Codd's work became the relational theory of databases. Most modern databases, and the SQL language that is used to query them, derive from Codd's pioneering work. Codd's revolutionary idea was that you can operate on datasets in the very same way as you can operate on numbers, and crunch data in the same way as you crunch numbers. Instead of having operations such as addition, multiplication, subtraction, etc., you would have operations that apply to datasets and transform one or several datasets into a new dataset in the very same way that when you add two numbers, you get a new number. Understanding that datasets are, in a database, some weird kind of variables is probably the most important concept to understand. There are several variants of the SQL language, and I'll mostly stick to what is common to all variants. In an SQL database, datasets are stored in tables, which are the physical embodiments of Codd's mathematical relations. You can imagine a table like a kind of structured spreadsheet. Tables are defined, filled, queried, and updated thanks to various commands that are all part of the language. One table is associated to each item you want to manage, and the columns describe different pieces of information that you can collect. For instance, a table may contain some information about people. One column will store the surname, another one the first name, a third one the birth date, a fourth one a picture, and so on. One row will associate pieces of information related to one person. That's where relational database comes from. The order of rows in a table doesn't matter, no more than the order of the columns. Whichever the order, it's still the same information. What matters is the association of the different pieces of information. Rows, columns and tables are just a convenient way to represent the association on a two-dimensional display, such as a sheet of paper or a computer screen. It is important that rows are not repeated. It makes no sense to store information in duplicate or triplicate about one person. I'm touching here on one of the numerous departures of the SQL language from the relational theory. In the relational theory, a dataset contains no duplicate by definition because each row in the dataset represents a fact, data that we know is related. A fact cannot be duplicated. If you insert twice into a table of movie stars information about one actor, it will not create a new actor that is a clone of the existing one. You will still have the same information in your database. The additional row will just pollute the database and give weird and probably wrong results in the programs that try to make sense of the data. Nevertheless, SQL, if you don't take care when designing your database, will allow it. The good news is that if you design your tables well, the database management system can enforce that we have no duplicates. We only need to create constraints in the database. That is, conditions that must be verified at all times and are enforced by the DBMS. Any attempt to violate such a condition will fail and return an error. In fact, no data can be either inserted or updated into the database if to do so would violate a declared constraint. In a well-designed database, each table has at least one constraint that says that two different rows cannot contain exactly the same values for, at worst, all the columns, and more commonly, for some of the columns. Those columns are collectively called key. To know whether a column belongs or doesn't belong to a key is a question of knowing if a different value in the column would mean a completely different fact, or simply an update that reflects a change of situation. For instance, in a table that stores information about people, replacing a picture by another picture would be an update. But if you assume that the current first name is correct, you cannot change it. You would refer to a different person. The first name is therefore a key column. It's obviously not the only key column, since several people can have the same first name. Therefore, creating tables isn't simply a matter of defining a structure in a database. You must also define constraints that ensure the quality of data. This is a very important point, because if we can be sure that data that is stored is correct and remains correct, that means that there are many checks that no longer need to be coded into programs. Programs become leaner, have fewer bugs, and are easier to maintain. Although the constraint that rows appear only once is arguably the most essential one, many other constraints can be defined. An important constraint is the fact that one piece of information is mandatory. Another important type of constraint is linked to the data type of each piece of information. All database management systems natively know numerical types, date and time types, binary types, character strings, and so on. Some of these types are very strict about what they accept as valid data. If you try to enter an invalid date, for instance June 31st, into a date type, you will get an error. You can also limit what you consider to be a valid range of values. For instance, you can ask the database management system to enforce that a number column will only allow values between 0 and 100 because the column will store a percentage that represents a fraction of something. Lastly, you can also ensure through another type of constraint, known as a referential constraint, that the values contained in one column belong to a set of values that has been acknowledged as valid. For instance, that a country or zip code actually belongs to a set of valid codes. When you query a database, you usually retrieve a subset where all the rows satisfy some common conditions. Although a column can in theory contain any type of data, including complex data, and even sometimes some user-defined types, you shouldn't use any type of data for filtering conditions. Databases often require indexes for performance. Indexes are data structures that, like book indexes, associate to a value the various locations where you can find it in the table. Most often, complex structures cannot be indexed. Besides, indexes refer to the full value in the column, like a book index contains full words or expressions. It's important in practice that when you express a condition, you can express it as an equality condition on the whole value in the column. Or, if some kind of ordering can be defined on the type of data, by specifying that the values must belong to a particular range.